Today we're going to start key features of functions by filling in this tree diagram on the bottom of page 6. Once I go over a specific key feature, I'll go and do an example and then come back up, talk about the next key feature, go do another example, so on and so forth. And then I'll do an example putting all of this together at one time at the end of the video. Okay, so the first key feature we're going to talk about is domain and range. From Math 2, you should have already, or you should be somewhat familiar with domain and range. Remember, domain is just a set of x value a function has. It is horizontal or left to right. Your range is a set of y values a function has, so the exact opposite. Y, think about it as your axes, is vertical or top to bottom or up and down. Okay, so I'm going to go to page 7 and I'm going to briefly go over an example just talking about the domain and the range of this top function. Again, domain is x values. So what I want to do is draw a vertical line, and I want to move this vertical line left to right, and where the graph touches this vertical line is the starting point of my domain. So again, I start on the left and I move it to the right, and I see that it touches here at that point. Now, this point is very interesting because it has an arrow on it. Because it has an arrow, I have to make a little exception. What this arrow means is that it keeps going and going and going all the way to the left. And the smallest number all the way to the left is negative infinity. And remember, infinities have to get parentheses. And then I'm going to continue to move my line across the graph. Right? Every dot, every piece of the graph is closed, so therefore it's contained in the domain. And I get all the way over here on the right, and I see it stops, but where it stops is an arrow. Again, because it's an arrow, I know it's going to keep on going and going and going and going and going to the right, all the way to positive infinity. Okay, so a note here if you want to make, up at the top, if a graph has arrows, then it goes on forever. Okay, also, if your graph goes to the edge, of coordinate plane, then you can put your own arrows. So an example of this will be this next one over here on the left. See how it goes to the edge? So it's okay for you to put an arrow on the left. Likewise, the furthest right piece of the graph, it's also okay to put an arrow because it goes to the edge of your coordinate plane. All right, so because this graph up here at the top of page 7 keeps on going because of the arrows, I know the rightmost x value is positive infinity. Again, infinities have to get parentheses. Now I'm going to move on to the range. Again, ranges are y values. Now y values, instead of using this vertical line, I'm going to use a horizontal line. And now, horizontal line, you want to start at the bottom because it will be your smallest or your minimum value. And you see it touches these arrows. Because it touches this arrow, it's going down, 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 all the way to negative infinity. And again, because it's an infinity, either positive or negative, it gets a parentheses. Now the biggest value is what we're going to call max. We'll get to that later. But I'm going to go all the way up, looking for open dots or until I get to the top of the graph, which is right here. So there. And again, this is my biggest y value of the graph. So I would have to plot this point. And that's -1, 8. And again, I want the y value. So 8. And because this dot is closed, it gets a bracket. Now going back up to the next key feature, we're going to talk about continuity. Okay. Continuous simply means there is no breaks in the graph. Another word you can use for break is gap. So there's no breaks or gaps in the graph, or undefined values for your y column. Okay. The exact opposite is discontinuous. And if a function is discontinuous, there are breaks or gaps. In the graph, or undefined values for your y column. So the easiest way to spot if a function is continuous or not is to actually start at the leftmost piece of your graph and put your pencil down. Then you just want to trace the graph. And if you can draw the entire graph without lifting your pencil, then it's continuous. Okay? So I would say this is continuous. I didn't lift pencil. Or there's no breaks in graph. The next one we're going to talk about is max and min. I briefly touched on this when we were speaking about the range. Your max is the highest or the biggest. Again, so you have high spots or peaks. Your min is the smallest or the lowest point a function has. And again, I would say low spots or valleys or dips. And then we have these things called the relative max or min values. And these are where turning points occur. Now, a turning point is very simple. So if I have a graph, a turning point will be here because, again, read the graph left to right. It's going up, it's going up, it's going up. When it gets to this point, it then changes direction. Okay. Likewise with this graph, it's going up, up, up. Now it starts going down, so I know a turning point would be right here. It's going down, down, then it starts going up. So I know a turning point will be there. Okay, so turning points are going to be anytime your graph changes direction. So over here, I have a turning point. And this point right here is also a max. And max mins, you want your y values, so at y equals 8. Your next key feature is going to be roots, zeros, or solutions. Your roots or zeros can be used interchangeably. I use roots and zeros when I only have one function. It will always be where the graph touches, crosses, or intersects your x-axis. Another way to spot this, if you're given a table, if it has a 0 in the y column. Okay, and solutions is when you have more than one function, so 2, 3, 4, 5. Think of solutions is when you solve, right? Solutions and solve systems of equations where the graphs touch, meet, or intersect. Okay, and for root solution zeros, we're always wanting the x values. Again, I have that down here at the bottom. Your answers to a solution is where your tables have the same y value. So roots are solutions to this question. Again, I want to find where it crosses, touches, or intersects the x-axis. So again, I'm going to go from left to right, and I see it touches right here. I keep on going to the right, and it touches right there. Now it's possible to have 0, 1, or 2, or 3, or 4 solutions, roots, or zeros. Right, the number isn't or may not always be the same. And again, I want the x value. So -3 and 1. So x at -3 and +1. And then last but not least is end behavior. So we see this again in Math 3. It is always the y value of function approaches as x goes to positive infinity and negative infinity. So basically, the way this is read, and this is what messed a lot of us up in Math 2, is this notation, right? X arrow simply means goes to. So as x goes to negative infinity, another way I like to think about this is the leftmost furthest piece of the graph. Does the graph point up or down? And then again, this blank is going to be dependent upon the graph. So if you have to write the way this one looks, x goes to positive infinity, or you could just say infinity. I like to tell or use the adjective positive to describe which infinity. Again, y goes to ... And again, it will depend if the graph is pointing up or down. So I'll put that in here. If your graph points up, y goes to positive infinity. And if your graph points down, y goes to negative infinity. Later on, we'll also look at tables. You want to use big numbers. I'm going to say a different word besides big. I'm going to say extreme. Such as negative 100,000 or negative 1,000,000. Like positive 100,000 or 1,000,000. And the y value it spits out there, you would use it, and if it's very, very big, positive infinity. If it's very, very small, negative infinity. If another value you'll see not very often in Math 3 will be 0, or it may change when we get to rational functions, but we'll cover that once we get there. And again, in behavior notation is always this way: x goes to negative infinity, y goes somewhere. X goes to positive infinity, y goes somewhere. So when I do in behavior, I always find the left piece of the graph and the right piece of the graph, and I'll put an L on the left and an R on the right. The left is always x goes to negative infinity. Well, is the graph pointing up or down? It's pointing down to this y value, negative infinity. X goes to positive infinity, or my right highlighted piece. So I come over here and I find my rightmost piece of the graph. If it's pointing up, it's going to positive infinity. If it's pointing down, it's going to negative infinity. So that's that example. And now I'm going to go ahead and go down to the bottom and do this one. So when you have graphs that have multiple pieces, what I like to do is do them piece by piece. Okay, so I'm gonna actually use different colors here. Let's have an orange graph. I'm gonna leave the middle one red. Then I'll have purple down here at the end. So domain of my orange it goes to the edge, so I can put a arrow. Then it stops. The red has a dot, so that means it stops. It has a dot here, which means it stops. Dot here, and then it goes to the edge over here on the right. So now, domain of just my orange piece would be from negative infinity to 4. It's got a closed dot, so it gets a bracket. Then my red function, I read my red function left to right. Its smallest x value is -4. It's open, so it gets a parentheses. And it goes all the way to the right. until it gets to 2. It's got a closed dot, so it gets a bracket. Then my purple starts at 2, but it's open, so it gets a parentheses. And then it gets to 4, and I have an open dot. So I stop at open dots. When you get to an open dot and you stop, it starts right back at the same number, okay? And then it's going to go to infinity, and infinities always get parentheses. Now, when you want to write this as your final answer, because this is very complicated to look at, you just simplify it. So the smallest 100% is negative infinity, and it goes to 4, okay? And I have 4 as a bracket. Then I have 4 as a parentheses. If you have a bracket, it's going to override the parentheses. So 4 bracket, 4 parentheses, -4, I'm sorry. -4, -4. So we go to -4, and it's going to still have your brackets. Okay. But now is the red one continues into 2, and it has a bracket. And the function to the right is also 2, but it has a parenthesis, so it gets overrode. So 2 is also included, and then it goes to 4. I have parentheses, then I have parentheses again. So that means I have to stop now. So from negative infinity to 4 cannot be contained. And then we say or it goes from 4 to infinity. So everything on the left got cleaned up and goes and becomes what's on the right. Now range, we're going to use a similar approach. Range is a little bit more difficult. So again, I start at the bottom where I can start with my orange graph. It's pointing down. So it goes from negative infinity and it goes all the way up until 4. Then red, smallest x value is -2. So open dot. And the biggest y value, we're just going to call this 5. I know it's a little over, but for this example, and again, if you don't see a dot, you can assume it's closed. Then we go to purple, again starting with the smallest value, which is negative infinity. And it goes all the way up until 6. And now again, I want to try and condense this like we just did domain. So instead of going left to right like I did for the domain, I want to go from my smallest value that I begin with. So out of -8, -2, and negative infinity, I want to start with the smallest, which negative infinity is the smallest. And then 6. I want to then go to look for my biggest. So I have 4, 5, and 6. Well, 6 is my biggest. I messed up on this range. For the orange, it should have been negative infinity. So guys, I make mistakes as well. It's okay. So negative infinity is the biggest, or excuse me, the smallest. And then 6 is my biggest. And it can be contained. Now I want to go make sure that I don't have any holes in my graphs. Well, if I look right here, I happen to have a hole. But because this hole is at this value right here and it's shaded with the dot, right? Again, if you don't see a dot, you can assume it's a closed one. It overrides this open dot. All right. And I would still follow that all the way until I get to right here where I have another open dot. And there's an open dot. So I'm going to draw a horizontal line and see if I ever touch another piece of the function that also has a closed dot at this same y value, which I do. And then same repeat process, which I do right here. So this is going to become closed because of this dot. This one is going to be a part of the range because of that dot. So essentially, this doesn't matter anymore. This doesn't matter anymore. This one down here doesn't matter anymore. It's overridden because there's a y value that is contained in the range. So the range of this function is negative infinity to 6. Root solution zeros, again, where does it cross the x-axis? There, there, and there. So you will say it has 3 at x equals, we'll say like negative 2.5. Um, 1.5 and 4.5. Be careful when you're writing your roots and solutions, because negative 2.5, 1.5, 4.5, if you write it like this, some people may think you're talking about a 3D coordinate plane, or excuse me, like a 3D graph. So if you're going to put commas in between them, make sure you use the squigglies, right? And what this does is just simply means set, where parentheses mean point when we're talking about values. Now in behavior, again, x goes to negative infinity, y goes somewhere, and as x goes to positive infinity, y goes somewhere. What's that somewhere? Again, I want to highlight the furthest most left piece, put a little note that says left. Then I'm going to go all the way to the right. And put an R. Again, if I can make a judgment that this arrow is pointing down, it goes to negative infinity. If I can make a judgment on the right arrow and say it's going up or down, then I know it's going to one of the infinities. If it's pointing up, it's going to positive infinity. If it's pointing down, it's going to negative infinity. I'm confident in saying it's pointing down to negative infinity. Now, as far as something being continuous or not, again, I want to start on the furthest leftmost piece of my graph, and I want to try to draw from point to point, or trace the entire graph without lifting my pencil. If you see here and here, I have this blank space that I wasn't able to go over without lifting my pencil. So we're going to say no, because it has gaps or breaks. And again, whichever word you want to use, that's just more for verification. Notice a little bit longer video, but these, this bottom example I did, you won't see a ton of them. I just wanted to give you an example because we will spend a couple of days on piecewise functions, and piecewise functions also have key features to them as well.